Well, hello, it's great to have you guys back. Tonight we're going to be discussing magnetic field. Here's our equations that we've been working with. We're going to be adding to these over the next couple of days. Things that we're going to be learning. For given situations, you're going to be able to predict whether magnets will repel or attract each other. Describe the magnetic field around a permanent magnet, and we want to be able to describe the orientation of Earth's magnetic field. Magnets. In general, magnets are going to attract iron-containing objects. Magnets have two distinct poles, called the North Pole and the South Pole. These names are derived from a magnet's behavior on Earth. And like poles of magnets repel each other. Unlike poles will attract each other. Magnetic domains. Magnetic domain is a region composed of a group of atoms whose magnetic fields are aligned in the same direction. It's called a magnetic domain. Some materials can be made into permanent magnets. Soft magnetic materials, for example iron, are easily magnetized but tend to lose their magnetism easily. Hard magnetic materials, examples that would be nickel, tend to retain their magnetism. Magnetic fields. Similar to an electric field, a magnetic field describes the behaviors of the north and south poles. A magnetic field is a region in which a magnetic force can be detected. Just like in an electric field, there was a force, and I'm going to draw a little picture up here of an electric field that we had. We said there was a positive charge and there was a negative charge, and we put a positive point charge in here. What would happen? There was this electric field that described the behavior of what this proton would do. It would travel to the right. It would be forced to the right. Well, magnetic fields are similar creatures. All right. Magnetic field lines can be drawn with the aid of a compass. This is a great example of a magnet. On here we've got a north and south pole. So here's our north pole, here's our south pole. And notice that the compass, all right, this would be our compass. The compass turns to be in correspondence with the magnetic field lines again. Once again, just like electric field lines didn't really exist, they were lines that we drew to show how a point charge would act. Magnetic field lines, the lines don't actually exist. They're there just to show us how a compass or something magnetic would react if put into that field. What I want you to realize here is that the field is coming from the north to the south. So the magnetic field goes from north to south. Earth's magnetic field is similar to that of a bar magnet. The magnetic south pole is near the geographic north pole. The magnetic north pole is near the geographic south pole. The magnetic south pole is near the geographic north pole. Well, why is that? Well, and the other question is, why is the magnetic north pole near the geographic south pole? Well, the reason they came up with that is, if you look at the Earth, let's draw the Earth here, we'll draw the Earth. We've got, the green mass, we've got some green here on it, and then, lots of water. I switched over here. So we've got lots of water here around the Earth. They stuck this magnet right smack dab here. And the magnet we had was north, and down here was the south. So the north pointed to the north. So what did they call it? They called it the North Pole because that's the way the magnet went, and they called this the South Pole. But realistically, think about what this says again. The magnetic South Pole is near the geographic North Pole. That makes sense because the north part of the magnet would be attracted to which part of the Earth? Its actual south magnetic pole. Even though this is what we refer to as the North Pole, magnetically, the South Pole is up here because the North would be attracted to the South part. And likewise, even though this is what we call the South Pole of Earth, magnetically, the North Pole is down here. And the North and South poles of these magnetically be attracted to each other. So, this was done a long time ago before they fully understood everything that was happening. They just knew they had a magnet. They knew this one side was the north, the other side was the south. When they held onto it, the north part of the magnet they were holding onto was pointing towards one part of the Earth, so they called that the North Pole. It wasn't until later on that they realized why the north part of our magnets were pointing towards what we were calling the North Pole, because it was actually magnetically the South Pole, so the north part of the magnet was attracted that way. And here's a good example of it. Magnetically, up here at the top, they're showing you that this is where the South Pole is. Even though this is what we would call the North Pole up here, right? The South Pole is magnetically up here, and so forth. Well, that ends our discussion today over north and south, over the fields, magnetic fields. What I want you to realize is they don't really exist. They're just lines to show us how a magnet would act when placed in that magnetic field. There is going to be a force because there is an attraction between south poles and north poles, so there is a magnetic force that we're going to be discussing. And that the poles on the Earth are actually flip-flop of what we call them. Even though we call the North Pole, magnetically, it is really the South Pole. The last thing I want you to see is, again, our magnetic field lines are going from the north to the south. Down here being the north, up here being the south. Hey, that's it for our notes today. I hope you enjoyed it. I know there were some things I know we discussed. You should be lots of questions. I'll see you on the flip side.